Good afternoon. Welcome back to the online sessions on AWP, antennas and wave propagations. In the previous session, what we discussed is we have completed about the half wave dipole antenna, and we discussed about the derivative part of the radiation resistance of a half wave dipole antenna, and also the radiation pattern of an half wave dipole antenna. So here in the today's session, we try to discuss some parts of the other types of the antennas, such as the loop antennas. In loop antennas, we normally going to have small loop antennas and large loop antennas. So we discuss both of them of loop antennas, and helical antennas. We discuss about helical antennas. So these loop antennas and helical antennas are preferably used to transmit the signals at medium and high frequencies at a microwave range, medium and high frequencies at a micro. Well, the shape of the loop antenna will be something like this, where we normally going to have a wire is normally taken. It is simply wounded just like a loop structure. So because of these various varieties of loop structures, we can have a loop antenna something like this, rectangular shape, circular shape, triangular shape. So like this, based on the applications, we normally going to have a different shapes of the loop antennas. So apart from loop antennas, we try to discuss about the helical antenna today. So helical antenna is normally going to be something like this, which is going to be of helix in shape. So helix is something like wounded round in a linear fashion, is known as a basically helix. So we discuss about these two types of the antennas. So once again, helical antenna is normally used to transmit signals at large frequencies. Now here, let us look into the loop antennas now. Basically, loop antennas are normally constructed by using linear conductors. So the conductors which we use in the loop antennas are going to be linear conductors. And these linear conductors are something like wounded round to form a closed loops in order to form a loop antennas. Now here they come with the two categories. One is going to be small loop antenna, other one is going to be large loop antennas. In small loop antennas, the basic difference is normally based on the wavelength lambda. So if one is less than one lambda wavelength of one, it is going to be small loop. If it is going to be equal to one, it is going to be large loop. So around 0.086 lambda wavelengths of wire is normally going to be called as a small loop category, and wave approximately a wavelength of one wavelength of wire is going to be of a large loop antennas. So these small loop antennas are normally used to transmit signals of low frequencies, and large loop antennas are normally used to transmit signals of high frequencies. So both of them are normally used to transmit the electrical signal and EM wave to be propagated from the output of the antenna to the far fields. So now here one more difference between these two, small loop and large loop, is going to be the circumference. So if the circumference is going to be lambda by 10, it is going to be called as a small loop antenna. So if the circumference of the antenna, total circumference of the antenna is equal to lambda, which is nothing but wavelength of the wave that we are transmitting, then it is normally going to be called as a large loop antenna. Now, the basic shapes of loop antennas can be multifold. Now, you can just have a one loop here. You can take a long wire and you can just simply wound it like a circle with two poles. Then you normally going to form a single turn circular loop antenna. Now, similarly, you can just have a rectangular kind of antenna where you can just have a loop, take a wire, complete single wire conductor, and this conductor is normally wounded something like this. Okay, it is wounded, and finally one more winding is normally taken from the other end. So it is going to be multi-turn, loop antenna. So like this, we can normally going to form different types of loop antennas in order to radiate signals to the far distance. So single loop, single feed antenna and multi feed antennas are normally being constructed. So these antennas, what the antennas normally going to have now, these antennas are normally going to radiate signals at a far field. So once again, loop antennas are used to radiate, large loop antennas are normally going to radiate signals at a far field. where this loop antenna is normally oriented vertically, and these are normally vertically polarized. So if at all we want to transmit a vertically polarized wave, we normally prefer the loop antennas to transmit vertically polarized wave. Now, all the antennas are normally going to radiate the EM wave with respect to the axis of the antenna. With respect to the axis of the antenna, we normally going to radiate the signal. So, all these signals are going to be simply vertically polarized signals by using the loop antennas we normally going to use. Okay. So, then after this, we normally going to have basic advantages and disadvantages of this loop antenna. A small loop antenna is normally used as a magnetic dipole. So here a loop antenna, small loop antenna can be treated like a dipole antenna. Already we discussed about dipole antenna. Dipole antenna's wavelength is normally going to be lambda by 2, lambda by 4, lambda by 6, lambda by 10, like that. So a loop antenna has directional properties, whereas a small vertical antenna has the same properties. A loop antenna is normally going to have directional properties, whereas a simple vertical antenna, something like a monopole antenna, has not the same directional properties as that of the loop antennas. So the induced EMF around the loop must be equal to the difference between the two vertical sides only. The induced EMF around the loop antenna must be equal to the difference between the vertical sides. So how much is the induced EMF? The induced EMF is simply difference between the two vertical sides of the loop antenna. So every loop antenna is normally going to have two sides. So that means a single wire is taken and two sides have been formed by using the by using the by using the wide construction. That means by just making them or winding them into a loop, we normally going to finally going to get two sides of the antenna. So that means these two sides difference would be taken, and the effective one is normally going to be the induced EMF around that particular loop. So no EMF is induced in case of the horizontal arms of the loop antenna. So in the horizontal arms, because it is vertically polarized, no EMF is normally induced. So now here the shape of the radiation pattern of the loop antenna is irrespective of the shape of the loop that we normally going to form. The currents are at the same magnitude and phase throughout the loop. So here in the loop antennas, the current which is normally going to be there is normally going to be same magnitude and phase throughout the loop while the wave is getting propagated through the antenna. Now, what are the drawbacks? The drawback is what? The transmission efficiency. The transmission efficiency of an antenna, the transmission efficiency of an antenna is going to be very poor. So it radiates less effectively the EM waves. It is suitable for low and medium frequencies and not for high frequencies. So the small loop antennas are normally meant for medium frequencies and low frequencies. And in loop antennas, two nulls of the pattern result in 180 degrees ambiguity. So here what happens is the two nulls, we normally going to get two nulls here of the antenna which are going to be 180 degrees apart. So loop antennas used as direction finders are unable to distinguish between bearing of distant transmitter and its reciprocal bearings. So loop antennas are not suitable for reciprocity theorem. That means it's not going to satisfy the reciprocity theorem all the time. So these are the various drawbacks of the loop antennas. And next is other comparisons we'll see in the next class about far field regions. Okay. Then finally we look into the helical antenna. So helical antenna is also going to be forming of a loop in a linear fashion. See this here, a loop is been formed in a linear fashion in the case of the helical antenna, where one of the internal, there is going to have two sides here. One side is going to be internal conductor, other one is going to be the outer conductor. It is something like a coaxial cable, where internal conductor is normally been wounded something like this to form a helix, and the distance between the two ends of the loop helix is going to be called as S, and A is equal to N into S, right? So here it's going to be a feed angle. So this angle is going to be the feed angle. So now the radiation pattern is also, now almost all the radiations are going to start from the origin point, and it will be maximum at a far field region. So this is normally used for far field radiations. And this helical antenna is normally preferred for high frequency and ultra high frequencies to provide the circular polarization. So here, in order to provide a circular polarization, we normally use the loop antennas, or helical loop antennas, or helical antennas. Okay. So here, the length L of one turn length L is normally going to be is equal to under root of s square plus pi d square, where s is the spacing between the two helix and d is the diameter, the diameter of this particular helix, and pi is a constant parameter. So using this particular formula, we can find out length of one each and every turn in this particular loop antennas. Okay. So this is what, using this loop antenna, using this helical antennas, we normally going to transmit signal to the far field. Okay, without much losing of the signal. So the efficiency of the helical antenna is going to be more in comparison with the efficiency of the loop antennas. In comparison with the loop antennas. Okay. So in this helical antennas, we normally going to come across two other varieties like resonant antennas and non-resonant type of the antennas. Well, this helical antenna is normally going to get operated in two modes. One is going to be the normal mode of radiation. Another one is going to be the axial mode of radiation. The normal mode and axial mode differs with respect to the dimensions of the antenna with respect to the wavelength that we normally going to use to transmit. So in the normal mode of radiation, when the dimensions of helical antenna are very small compared to the operating wavelengths, then we normally call this as a normal mode of the radiation characteristics of an antenna. So the radiation fields of helical antenna are similar to the loop and short dipole antennas. So helical antennas is equivalent to a small loops and short dipole antennas connected in series. So that means, in the already we have discussed about this E5 value, okay, which we have to remember this particular formula. Same formula we normally going to refer here also. But whereas here the dimensions here are with respect to the dimensions of the helical antenna. Something like A is nothing but area of the loop, which is nothing but pi d square by 4. I is nothing but the retarded current, which is going to be 10 sine omega t minus r by c, which is nothing but retarded current, and r is the distance. Total r is the distance, radial distance here, and d is the diameter of the loop that we are considering. Lambda is the operating wavelength. So the axial ratio which we can calculate is going to be e theta by e phi. So once we know e theta, we can find out e phi value based on the intrinsic impedance formula. The next one is axial mode of radiation. This axial mode of radiation is normally done when the circumference and spacing s are of the order of one wavelength. So that is what the basic difference. When the dimensions are small in comparison with wavelength of the signal we are transmitting, it is called normal mode. When the dimensions of the helical antenna are in the order of one wavelength, then it is going to be called as the axial mode of the radiation pattern. So the general expression for terminal impedance here is going to be 140 C by lambda, where C is nothing but circumference of the helical antenna, where lambda is the wavelength of the wave that we normally going to transmit. And one more formula we have to remember, this derivation is not there in the syllabus, just remember the formula. Half wave beam width is nothing but equal to 52 by C under root of lambda 3 under root of lambda 3 by n into s. So this is what the basic formula to get the half wave beam width, where c is the circumference, lambda is obviously wavelength, n is the number of turns, and s is the spacing between the two helices. Okay. So the axial ratio is nothing but equal to 1 plus 1 by 2n. Now in this, we are going to have two variants here. One is resonant type of the antenna, another one is going to be called as a non-resonant type of the antenna. So in the helix, we are going to have two ends. One is going to be the transmitter end, another one is going to be the receiving end. So this is going to be one end, this is going to be the another end. So now, based on how these two ends are normally constructed, we normally going to have a resonant antenna type and non-resonant type of the antenna in the helix antennas. So here, what about this resonant antenna type? Now in the resonant antenna type, the transmission that is in the correspond to resonant antenna line, that is exact number of half wavelengths along and is open at both ends. That means this end may be transmitted as a transmitting end and receiving end. Similarly here also this side. So the waves which are going to be opposite to each other, that means if this end is transmitted end and the wave is getting transmitted, and the same similarly if this end is working like a transmitter, this is working receiver, and the wave is being transmitted in the reverse fashion. So that means here these two waves are normally going to form a standing wave kind of a pattern, and the half wavelengths, these two are normally going to have same half wavelengths. This entire line is normally going to have the same half wavelengths. Because of this reason, because of this incident and reflected waves are normally going to form a standing waves, and hence the standing waves are normally going to exist in the resonant type of the antenna, because both ends are normally going to have same amount of impedances. Okay, it looks to be same at either ends, so therefore it is normally going to form a standing waves. Whereas coming to the non-resonant type, here the transmission line that is excited at one end and terminated other end with a characteristic impedance. So this end, this z naught is nothing but characteristic impedance, and at one end it is simply excited, okay, with a normal kind of a transmission, with a normal kind of a resistance. Whereas here other end is going to be compulsorily the characteristic impedance at the other end. So in that case, the waves which in been transmitting to and fro is normally going to be of different half wavelengths. Now, due to the absence of the reflected waves, standing waves do not exist. Here, because of this reason also, we can say the standing waves are not going to exist in this particular type of the pattern. So the radiation pattern of this antenna is simply bidirectional radiation. So it's going to be bidirectional. That means it is two-way. Radiation can be done, from this side as well as, okay, this side can be radiation, this side can be reception. So from either way, we normally going to have the radiation. So therefore, we can say that uh, this end is normally going to radiate some amount of radiation. This amount is also normally going to radiate some amount of radiation. So thereby we normally going to get a bidirectional radiation pattern, and the patterns normally looks like this, something like this, where it's going to be a bidirectional. It's going to be bidirectional. Two ways is normally going to get radiates. Now, whereas here the radiation pattern of the antenna is unidirectional, only in one direction it is normally going to radiate. Okay, so this is for one radiation. This end we normally going another radiation. So at two ends we normally going to have a radiation pattern, right? So these antennas are used for variable and wide frequency operations. Now non-resonant antennas are normally preferred for variable and wide frequency operations. So the operations which we normally going to perform for wide frequency and variable frequency antennas, we normally go with a non-resonant, and obviously resonant antennas is normally going to be non-variable antennas, non-variable frequency antennas. So therefore it is going to be fixed frequency antenna, something like a LC oscillator. So in LC oscillator, if L and C are fixed, we can transmit signals of a fixed frequencies that is operating at resonance. So they are going to be called as a fixed frequency kind of a thing. So therefore, these are called as resonant antennas because both the sides are resonant to each other. Whereas here they are non-resonant because we can be, because both the sides are the impedances at both the sides are not same. Therefore, they are going to be non-resonant type of the antennas. Okay. So therefore, the resonant antennas are normally going to show a bidirectional radiation pattern, whereas this one is going to show unidirectional radiation pattern. So this side is going to radiate, this side is also going to radiate. That means two directions are there here. Here only one direction we normally going to have. So therefore it is going to be unidirectional antennas, and the resonant type of antennas are known as the bidirectional type of the antennas. Okay, with this, we'll end up with this loop antennas now and helical antennas, basic theory that we have. Okay, in tomorrow's class, we go ahead further, okay, and deal with some of the types of the antennas which are there to write a short notes in the examination. Thank you very much for the today's session.